right. Hi, everybody. I am Wilder Lopes, and I'll be presenting this work called Clifford Convolutional Neural Networks for Lymphoblast image classification. So just a quick question. Who among of you has experience with neural networks designing and training? Any? All right, that's good. That's good. I believe that's one area where geometric algebra can really contribute. And we're just in the very beginning. So the goal of this paper here is to showcase the capabilities of Clifford algebra neural networks for a very specific application. So I must say that my co-authors did most of the work here. They are already working on this for a while. And my contribution is based on my experience in deploying Clifford algebra neural networks in industrial environments. So I built a whole company based on this. So I will be talking more about this on Wednesday. So for this paper, I won't be focusing too much on the mathematics. As I said, I want to showcase the capabilities of Clifford algebra neural networks. So we picked this application, which is the classification, the image classification for the diagnosis of acute lymphoblastic leukemia. And we're going to be going through this in a minute, and we'll show the classical approach, which is based on convolutional neural networks, and then how hypercomplex neural networks can help improve not only the results, but the way we train the neural networks and make them smaller. Then I'm going to compare this to the previous work that my co-authors did, and also the state of the art currently. And I will gladly discuss some potential future developments because there are many interesting things that could happen here. All right, so let's move on. So what is acute lymphoblastic leukemia? This is a very rare type of blood cancer that's usually seen in children and can be lethal if it's left unchecked. So obviously there is an appeal here to improve the diagnosis of this kind of cancer. So currently this is done by analyzing an image. And when I say analyzing, I mean there is a person who looks under the microscope to see how those cells are looking like. It's very costly, obviously, because most of it is done manually and it's prone to error. So what we want to do here is to try to develop a system that could make it automatic. One benchmark data set that's available today is this all-IDB that's maintained by the Department of Computer Science of the University of Milan. And this is a very standard data set that people use in order to benchmark neural networks in this. Yeah, and then it's important to show here that the picture on the left is the one that we are looking for. So this is the one that we want to identify with our neural network. So the classical approach, convolutional neural networks. So for those who don't know, but I believe you all heard about the convolutional neural networks and what they can do for us. So in 2012, there was finally this explosion in the field of deep learning. And then everybody started using convolutional neural networks to do image analysis. So today, this is a staple of any kind of signal processing that that's built to analyze images. So one classical way to analyze images is to just build several blocks of convolutional neural networks, put them together, and feed the images to those blocks. You will find several different variations in the literature. Some, for example, you will see ResNet, VGG, so you name it. There are many different neural networks out there that are based on this convolutional layer. And this is very, the reason for why this is so widespread is because it really works. It's easy to perform, like it's very light compared to the dense neural network alternatives, and it's easy to implement. You're finding libraries such as PyTorch, TensorFlow. So this is what people use today. Now, if we think about, can we transpose this and put this in a Clifford algebra space? What would happen to a neural network if instead of using weights that are real valued, if we start using Clifford algebras or multi-vector valued weights? So obviously there is a lot of mathematics here, and I'm not going to be focusing on this today. I'll be happy to talk about this on Wednesday, but the basic thing we want to benefit from Clifford algebras is the fact that the multi-vector in this sort of applications becomes the unique unit of information. So you can do everything by operating on multi-vectors. In this case here, for example, let's say that you have a RGB picture. An RGB picture is just like a stack of 3 pictures, one in the red spectrum, another one in the green spectrum, and the third one in the blue spectrum. So what a CNN does in the classical way to solve this problem is to look at the red channel and then go again, looks at the green channel, and again looks at the blue channel. So it's actually analyzing each channel separately, which is not very wise because we know that there is a correlation between those channels because it's a unique picture of the same thing, just represented in different spectrums. So what if we could analyze that inside the same unit of information? So there's this trick that's actually used way before deep learning. People were working with quaternions in signal processing. They used to do this, like they get the pixels and they allocate them inside the imaginary parts of the quaternion in this example. If you have pictures that have more than 3 channels, for example, if there is anyone who worked with satellite images here, you know that there are several different channels. So you can do the same. You're not going to use quaternions. You can use a higher dimensional algebra, and then you will allocate the pixels there. So by using this trick, you make the multi-vector your main unit. Then you are in this space. So now you can use geometric calculus. You can just like elevate everything that you were doing in real valued algebra to Clifford algebras. Of course, you're going to have to re-implement the backpropagation operations using geometric calculus, which is very interesting, but things work. So there is this publication here by Granero et al. From last year, where they applied a quaternion valued CNN to benchmark this all data set, and they obtained a very nice performance. So my co-authors did a previous paper where they got that same neural network and put them in a quaternion format, and they were able to obtain very good results. So what we want to do here is to go from quaternions to other Clifford algebras. Again, this is a very, very small example. We are not exploring several different algebras, but it's just a beginning. The intention here is to have several different papers that can explore different algebras. So for this paper specifically, we focused on these 4-dimensional Clifford algebras and tried 3 of them. However, myself, in my own work in the industry, I design neural networks for several different algebras, not only 4-dimensional algebras. So that's something that's, once you have the core well established and a code that you really trust, you can simply scale it. But as Chris was saying earlier, like it's very hard to make stuff that computationally efficient. So how do we implement the hypercomplex-valued CNN? So there are several different ways to implement this. Personally, I prefer the C++ approach because that's what I'm used to. I've been doing this for several years. Nevertheless, because Python now is so popular, there are many people implementing their own libraries in Python and using other ones that are out there. The choice that we took for this work was if we have a matrix with multi-vector entries, we can actually break it down into several different matrices with real valued entries, and then allocate them to each one of the imaginary coefficients and the one coefficient there. So this is one technique that you can do in order to translate the Clifford algebras into the matrix representation, but there are other ways. This is just like this one that's easy for research. It's definitely not the best one for computational performance, but it works very well. So the basic architecture, here I compare in this table the differences between the real valued and the Clifford neural networks. So we implemented two versions of the Clifford neural networks. One is the one we call equivalent, that in the end is going to have more or less the same amount of trainable parameters as the real valued one. Why this is important? Because we want to compare like apples with apples, like how much computation is going to take to train a neural network that's Clifford valued but has the same amount of parameters. And then we implemented a smaller version that has roughly 1/3 of the parameters of the equivalent version to showcase a very nice capability of Clifford valued neural networks. And I'm going to be talking more about this in a few slides, but when you have Clifford algebras inside the neural network, you can afford reducing the total size of the neural network, generating a final network that will deliver somewhat the same accuracy performance, but with much less parameters. This has a huge relevance for the industry because if your neural network is smaller, you perform less multiplications, you use less power, and you can deploy this in low power devices. So just like a little picture here illustrating how this architecture is assembled. So we have the convolutional layers, then usually we do this flattening at the end in order to do the binary classification between a cell being a lymphoblast or not. Another very important point, and this is something that other works have been exploring as well, is the encoding of the image. So for our results here in this in this data set, the best results for the Clifford algebra neural networks were obtained using the HSV encoding. The RGB encoding is obviously the most popular one. So if you're going to go and train your neural network with public data sets, that's the kind of encoder you're going to find. But using the HSV, which is a better model for closer to how the human eye perceives color, we noticed that the Clifford algebras, they perform better in this data set. It's not like more than 2% better, but still it's something that's significantly better to make us go through the work of converting into HSV. So this is a pre-processing step that we do before feeding the data set to the neural network. Now to the computational experiments. So the all-IDB data set has only 260 images. And for those who are experienced with deep learning, you already know that this is very, very little data to work with. And the split is traditionally done 50-50, 50% for training, 50% for test, which is not very usual in the deep learning community, but we kept like this because the previous work were using this split. So we wanted to be fair and compare in the same scenario as they used before. And we did a resizing to 126 by 126 pixels and some augmentations such as horizontal and vertical flips. We ran 300 epochs with the Adam optimizer and then other parameters, like you can read it in the paper. So we trained seven neural networks, 7 Clifford algebra neural networks. Sorry, 7 networks, 1 real valued CNN and 6 Clifford valued CNNs. As I already mentioned in the previous slide, we have the versions that are the smaller version and the equivalent version. And the use of compact networks contributed to reduce the risk of overfitting, which is something that you always have if you have such a small data set. So if you get this data set with 206 pictures and you use a so-called state-of-the-art neural network such as ResNet, you're going to be really prone to overfitting. It's very hard not to overfit. So you need to reduce the capacity of your neural network. And the best way of doing this is to reduce the amount of parameters. But doing this with the ResNets is very complicated. So you need to redesign from scratch. That's why we did this here. And another important point here related to the encoding is that the real-valued CNNs performed best on RGB images, while the Clifford algebras performed best on HSV encoded images. So here just two charts to illustrate that. As you can see, the Clifford algebras here like perform slightly better, slightly between 2 to 4%. And this might seem like very small, but it has a huge difference when you're dealing with diagnosis. So, I mean, I can keep talking about this the whole week, but there are groups even in Stanford, they are using complex-valued neural networks to analyze MRI images. And only 2% of improvement in accuracy can already represent like a huge savings in cost and also saving lives. So they're really looking for those scenarios where you can improve 1 or 2%. And complex-valued neural networks and Clifford algebra neural networks can be the path for this, can offer a path for this. So here are the numbers. As you can see, like you have a very small neural network, 3.3K parameters. So for those who know neural networks, this is very, very, very small. So you can deploy this anywhere, virtually anywhere, and you obtain a performance that's good enough in order to do, in order to perform this job. Of course, here we are talking about a healthcare application, but this kind of reasoning can be translated to other applications as well. Applications where you are performing some sort of classification in the wild, such as, for example, if you want to deploy this in a car or in a mobile device. So, all right, so if you want to play with it, this is available on this website. So please let me know if it's working. So you can try it out, see the implementation in Python. It's everything there in a notebook, everything in just one notebook to make it easier. But we are also making it available in a GitHub page. And hopefully in the near future, we're gonna have like a better organized module so people can install it. I'm also like have my own work on this, where I have a Python library that's a little bit more sophisticated and a little bit more optimized to design neural networks using TensorFlow. All right, so we arrive in the conclusion here. So we implemented Clifford CNNs for 3 algebras, but it's not limited to that. We can really scale this to any kind of algebras. 2 very important points here. The image encoding, you need to pay attention what is the encoding of your neural network, because it can give you it can be the difference between a poor and a great performance. And the choice of algebra. In this work, the algebra that performed best was the one related to the co-quaternions. But this could change depending on how you encode your data and depending on how you train it. We didn't do experiments with different splits, for example. This could change the results. But the main idea here is that the 4-dimensional algebras, the Clifford algebras, are delivering results that are, if I come back to the table, that are roughly 2% better than the real valued. And this makes a huge difference in the wild. So the Clifford CNNs outperformed the real valued CNN using only 35% of the real valued parameters. So again, this is another thing that is very important because this means that you can deploy this anywhere in low power devices. For future work, so we are currently talking about several different topics, but we really want to continue the theoretical analysis of the Clifford CNNs. That's something very important in order to understand how those neural networks behave. This is actually a challenge even when you're not in the Clifford world. Even like the analysis of neural networks in real valued algebras is still something that's not really solved. And another topic is to expand the work to encompass high dimensional algebras and higher dimensional image data sets. As I already mentioned, satellite images. There are several works from different groups. There is a special group, I think it's at the University of Tokyo, that's applying Clifford algebras to analyze synthetic aperture radar images. And it's really, really like amazing the results they are getting just by changing the algebra. They are not using fancy architectures. It's just like instead of using real value algebras that will analyze the channel separately, they are doing this using Clifford algebras. All right, that's the end. So thank you so much. Glad to answer.
Thank you, Wilder. Oh. No, there's plenty of time for questions. Yeah.
I happen to work in MRI, and MRI is naturally represented as complex numbers. So we were always putting in like real and complex or magnitude and phase. But then at some point, I think the group you mentioned started treating the numbers themselves as complex. And the gain came from changing the activation functions so that they operated on complex numbers in a novel way, not just ReLU. So how does that work here?
Yeah, that's another point I forgot to mention. The activation functions in Clifford algebras are very tricky. So what people usually do is to do the split activation, right? They get the ReLU and they apply to the real part and the complex part, sorry, the imaginary part. So this works up to a certain point, but previously I have things that I didn't publish that was part of my company's intellectual property. We were making our own activations in the Clifford domain.
And you're not going to tell me.
Oh, I may tell you. I'm in the process of making that public.
Okay.
So we can definitely connect and let you know.
Thank you.
I'm going to ask exactly the same question. Loads of questions. Joe's asked loads of questions.
Thank you so much. It was very, very clear. I wanted to ask first if you've seen Microsoft Research in Amsterdam published a paper about Clifford neural networks. Oh. And I wanted to know whether how your Clifford neural CNNs and their Clifford layers compare.
Sorry, who was the group?
I think Microsoft Research.
Oh, okay.
No,
I didn't see it. Was it recent?
Yeah, a couple of weeks ago, actually.
Okay, so I definitely didn't see it. So I would love if you can show me the link.
And the other question is, I think the advantage of using this Clifford description is that you have some geometrical information used in instead of splitting it into channels. What's your intuition behind why this works better for HSV color space rather than RGB?
Right.
Because
yeah.
The spatial correlation between different channels here is less intuitive, probably compared to other.
Right. Yeah.
Problems.
So this is actually use the right word. It's like I have an intuition. That's why we want to do the mathematical analysis and see if we can prove that. But the intuition comes from the fact that there is a mutual information, a correlation between the imaginary parts that's lost if you just break them down. So you can see this, like I started seeing this in my previous work that wasn't with neural networks, but with adaptive filters, which are basically gradient descent instances. So if you are performing, for example, linear prediction, you have several samples here, and then you want to predict the next one. If you do this, and if you are doing like the sensor fusion, and you have several different sensors. For example, you're trying to estimate how an airplane moves. So you get like the accelerometers, the gyroscopes, pressure sensor, and you put all of this together in a big multi-vector. You're going to have a better performance because you are processing all of them together. So my intuition comes from the fact that with the multi-vector, we can benefit from this mutual information, which is a concept from information theory. But I never had the quality time to sit down and actually write everything to prove this. That's the intuition.
Yeah, thank you.
Great talk, thank you. This is Eric Weiser. Question about your parameter counting. Are you considering?
Sorry,
question about your parameter counting.
Okay.
Are you considering your multi-vector to be 4 parameters?
In this case, yes.
Okay.
In this case, yes.
And then the other question on the slide about HSV, can you elaborate on that equation with the cos and the sine, and if there's any intuitionistic meaning behind that?
Well, my intuition, this was more like came from my co-authors, but my intuition is because it's a polar representation.
Okay.
So you naturally have this geometric information there. It's not like just numbers like it is the RGB. You have this relationship between the numbers from 0 to T255. So I think that's my intuition here, but my co-authors could answer this better than me.
Okay, great, thank you.
Hey, more for a general question. So maybe my information is a little dated, but cancer has historically been quite difficult for artificial intelligence, partially because genetics are very different depending on where people grew up and what their origin is. And then, of course, cancer types are very different. So could you just comment on, is that for that specific type not a problem, or is it still a huge problem in cancer research? Because most often, it still required human interaction afterwards, or someone manually checking the outcome. So what's just the current status, just an update?
Right, yeah. I know that from people who work in these areas, like every person is different, right? So if I have a method that performed well in this data set, there's no guarantee today that it will perform well for a given patient. So the intention here is not to make a tool for, at least not right now, to make a tool that can be deployed in a hospital, but to use and showcase, to use this data set and showcase that it is possible to improve the accuracy in comparison to the real value. If this is going to become a real product, we don't know yet because of this problem that you just mentioned.
Just one final question, comment. You refer to G11 and G20 as co-quaternions, but they're not quaternions at all, are they? They're just
it's just like the popular name that they are calling co-quaternions, or there is the split quaternions or
they're not quaternions.
No, I know they are not, but it's just like the popular name that people have been calling it.
We should fight back against that. They're just geometric algebras. So.
Yeah. No, and it would have been maybe better to just like talk about each algebra separately, but the 1, and the 2, they give similar results because they just differ.
They are the same matrix.
Exactly.
Brilliant. Thank you.
Thank you.